Hey everyone. So today what we're going to be learning is addition reactions with amines. But first I want you to recall the generic mechanism a uh, with a carbonyl group and a neutral nucleophile. So we had two different generic mechanisms, and one of them was with a strong nucleophile that was negatively charged, and now this one with a neutral nucleophile. And this required the presence of acid. That carbonyl oxygen is going to go get protonated first. Now what happens is after this is the formation of an oxonium ion, that positively charged trivalent oxygen. And what this does is it creates a more electrophilic site for that, and that carbonyl carbon is going to be that site, as I indicated in red. This is going to be more susceptible to nucleophilic attack now. And so this weaker neutral nucleophile can attack them, kicking those pi electrons up to the oxygen to neutralize that. So, sorry, I did not indicate that this reaction is going to be in equilibrium. So we want to make sure that we're using our equilibrium arrows for all of the mechanisms. Now this tetrahedral intermediate is going to have a positively charged nucleophile now, which obviously we want to neutralize. And so the way we're going to do that is by deprotonation with a base. And so typically that's going to be the amine. And so, or in this case, for the addition reactions with amines, it's going to be the amine, because amine is going to be more basic than water. However, water is basic enough to remove that proton as well. So after the removal of that proton, we get the desired product, which, depending on the nucleophile, can have a variety of names. But as we'll see for amines, it will be called a carbanolamine. So one thing we're going to have to note is that this is a generic mechanism. And so sometimes, depending on the nucleophile, we will get this alcohol product. However, when it comes to amines, we'll see that we actually get a variety of different products, and that's just because the nature of the nucleophile, as well as the intermediates that form and the conditions they're under, the reaction conditions. So let's take a look at review our amines. So first, the most basic amine is going to be ammonia, NH3. We can also have an amine with one R group, an amine with two R groups, as well as an amine with three R groups. And so these are going to be classified as primary, secondary, and tertiary. And we'll see that the ammonia and the primary amine, as well as the secondary amine, react differently and form two different types of products. And the tertiary amine actually just does not undergo addition reactions with carbonyl carbons. So we're going to put a little box around our ammonia and our primary amine just to show that those guys give a different product, and then our secondary amine will box that up as well. And so we're going to go over these different types of reactions right now. So the reaction conditions are typically going to be best under mildly acidic conditions, and so this is going to be the addition of a strong acid typically, but just a little bit to bring the pH down to about 4 or 5. And you'll see what this is essentially just a catalytic amount of acid, and just to get the reaction going, as we saw in the generic mechanism for addition reactions with neutral nucleophiles, which amines are. Okay, so let's take a look. We have a cyclic ketone here with ammonia, and we got our equilibrium arrows, and this is just a generic way of writing we have an acid. Okay, just H plus in brackets. So what we're going to do first is use that acid to protonate that carbonyl oxygen. And so again, what this is going to do is form that oxonium intermediate where the oxygen is positively charged. Then this results in the pooling of electron density from the adjacent carbon, thus making it more delta positive, this carbon in red. And since it's more delta positive, it's more susceptible to nucleophilic attack, and a weaker neutral nucleophile can kind of proceed with the mechanism. And so that ammonia attacks that carbon, kicks the pi electrons back up to the oxygen to neutralize it, resulting in resulting in this tetrahedral intermediate, which then can be neutralized by the presence of the amine itself, because that is itself a base. And so we neutralize this intermediate as follows. Now, resulting in a neutral tetrahedral intermediate. Okay. So now in the generic mechanism, this is actually where we finished. We have the alcohol with the OH. We also have the nucleophile on there, -1 proton. And as I stated before, this intermediate is called a carbanolamine, and is in fact just that. It is an intermediate. So since we are under mildly acidic conditions, we can protonate things, and since we have really good electron donors such as the nitrogen with pi electrons, we can protonate this OH group, making water, which is a great leaving group, and it can be forced out by the formation of a carbon nitrogen pi bond. So first we have our intermediate here with the positive, with the water, or set up for water to leave. Now formation of that pi bond with the nitrogen's lone pair will kick that water out and form something called an iminium ion. So now this iminium ion is an intermediate, as the nitrogen is positively charged, and so in order to neutralize that, we remove the additional proton with the base that's present in solution, and we get the final desired product, which is an imine product, where we have a carbon nitrogen double bond, a lone pair on that nitrogen, as well as one group on the nitrogen as well. In this case, since we use NH3, that group is a proton or a hydrogen. Okay, so we have seen this imine product before. We saw that as an intermediate when we were reducing amides with lithium aluminum hydride. So keep in mind that this imine product can also be isolated and then reduced to an amine with lithium aluminum hydride. So the product with the addition of ammonia or a primary amine to a carbonyl group is going to be an imine, but we'll see shortly that the secondary amines form a different product. So let's take a look at the reaction with a primary amine and see how it yields a similar product and what that really looks like. So we start with that ketone as well as a methylamine, in this case is our primary amine. We get that acidic conditions with HCl, which again can be abbreviated with H plus to achieve that pH of 4 to 5. Sorry, a little bit of editing here, but what you can see is that we will get the imine product with one methyl group on there. What we also see is that we form water as a byproduct, because that oxygen has to leave. And since we are forming water, and it is in equilibrium, if we remove that water, that's going to be a driving force. This is going to drive the reaction forward, favoring the products in this particular equilibriums. And the way we can do this is remove water with a drying agent, or we can use something called Dean-Stark trap. So we are familiar with molecular sieves in lab or sodium sulfate, but Protidine Stark trap is essentially just heating a reaction to boil off water and only collecting water. We'll see this again for acetals. So with all this talk about secondary amines forming different products, what we want to do is just give you an example of what the outcome's going to be. So we can use cyclohexanone again, the cyclic ketone that we saw before, and then our secondary amine can be a variety of amines. We just have to have two R groups on that amine. Some really fun ones are going to be cyclic amines, which we'll see in some practice problems. But in this case, we will use ethylamine. And with the addition of HCl, we will get our final product. Now, as drawn here. So this is obviously different. This is no longer a carbon-nitrogen double bond that would give us our imine product. And this is something called an enamine. Say what? So what the heck is going on over here? All right. So let's take a look at the mechanism. So first, we have a carbonyl, and we need that to leave, right? As you can see, that's not in the final product, so we need that oxygen to leave. And the way we're going to do that is make it a good leaving group. So first, protonate it with the acid that's in solution, making the oxonium intermediate, which then creates the more electrophilic site labeled in red. And now our weaker neutral amine can attack that carbonyl carbon to neutralize the oxonium, as well as forming a new charged intermediate. This tetrahedral intermediate, as shown here, we're going to go ahead and abbreviate the ethyl groups just for clarity. So now we're here with a positively charged amine, and we have our neutral OH there. So this is going to be an extremely common step that we'll come across. And so what we want to do is actually simplify this, because what we're going to do is remove the proton from the nitrogen, and then we're going to add another proton to the oxygen. So essentially what we're doing is shuffling protons around to create the water leaving group. And so as we remove that proton from nitrogen and add a proton from oxygen, we can call this a proton transfer. And instead of drawing those two separate structures, what we can do is just abbreviate it. And so if we look at our generic mechanism above, we'll see that the actual steps that I'm talking about. We have this positively charged ammonium circled in red, and we're going to remove that proton, and then we get this carbanolamine, and then we add a proton to the OH, giving us that water leaving group. And so again, those steps right there are going to be abbreviated as a proton transfer. Now, it's important to note that a proton transfer is not typically viewed as an intramolecular transfer of protons, so that oxygen adjacent to the nitrogen it's not well accepted to have that just grab a proton from the adjacent ammonium. Okay, so that's why we do have multiple steps to indicate that proton transfer, which we are now going to abbreviate. Okay, just to save us some time. So now that we have that water leaving group, we have the nitrogen lone pair come down, form that carbon-nitrogen pi bond, kicking the water out. Okay, and what this is going to form is a positively charged nitrogen, and this, we have seen this before, is an iminium ion. Since we do have a positive charge on that nitrogen, it's not going to be viewed as a stable product. And so we do have these adjacent hydrogens, however. And these adjacent protons are actually needed in order to form the addition product with a secondary amine. The reason why is because these protons are actually very acidic, being next to an iminium ion. If we were to remove one of those protons with let's say an amine, we could create a carbon-carbon double bond. This is similar to carbonyl resonances, right? And so that carbon-carbon double bond forms, kicking up the pi electrons to the nitrogen, thus neutralizing it. And what this results in is our desired enamine product. So this enamine product is called an enamine because we have an alkene. We also have an amine. So they just jam the two words together to give you the fancier sounding enamine name. And so this is the difference. It is subtle difference, but it is a difference between the secondary amine product as well as the primary or ammonia amine product. Okay. So let's take a look at some real life applications. In our eye, we have rod cells, and this would be as in cones and rods to help us see in the light or the dark. We also have cis-retinal, which is a highly conjugated aldehyde, and this aldehyde, in the presence of an amine, can undergo an addition reaction, forming an imine product. And in our eye, we have an amine source from an enzyme, an opsin, and when we form this imine product in the presence of light, we can actually isomerize this highlighted red cis bond to a trans bond. And so what happens is that we change from a cis to trans or bent to linear, and we have an electrical impulse in our brain that results in a visual image. Super cool. Speaking of a visual image, here's an image of that transformation. So notice we have the rod cells, we have the plasma membrane of the eye, and all that explanation. One thing we need to note is that opsin, or the cis-retinal bound to opsin, forms something called rhodopsin, and that's the compound, the imine product that shifts back and forth between cis and trans in the presence of light. And sorry, it looks like I missed a methyl group, so I'll go ahead and correct that. We'll add the methyl group. Not super essential, but just for good measure. Thanks, bye. So this is actually one of my favorite condensation reactions, or imine reactions, because of the isomerization aspect and how that results in an electrical impulse to form a visual image. That's cool stuff. But notice how all of our reactions were equilibriums, and so that means that this reaction is reversible. And so this reaction done in the reverse is called a hydrolysis reaction, and is called a hydrolysis if we break that word down, because we are literally, it's like hydro, water, lysis, like as in a cell lysis where you split the cell. And so we're splitting up water to form a new product. So if we have an imine in the presence of acidic water, we will undergo hydrolysis to form a ketone as well as the starting amine. And so in this case, we have this imine product, or imine starting material, in the presence of acidic water, and we get cyclohexanone as well as our primary amine. So let's take a look at the mechanism behind this. So since we have acidic water, we have a lone pair. What we want to do is protonate that nitrogen. We're going to use that lone pair to create a reactive intermediate. Since we have this iminium ion, this positive charge on the nitrogen creates a more delta positive charge on the carbon adjacent to it, and this makes it more susceptible to nucleophilic attack. Nucleophilic attack by what? Well, we have water in solution, and so water is a nucleophile, and so it attacks. And this results in a tetrahedral intermediate, where we have an amine, or it's essentially, it's pretty close to our carbanolamine, except that OH is protonated. Remember, we can undergo a proton transfer, removing removing hydrogen from the oxygen and then adding a proton to the nitrogen. This will result in, or pretty much sets us up for forcing that nitrogen or the amine to leave and creating that carbon oxygen double bond, which is in the final product. Sometimes it's helpful to look at the final product and to guide us through the mechanism, as we know we need to form a carbon oxygen double bond, and we also know that we need that nitrogen to leave. Well, how do we make it leave? We make it a better leaving group. And how do we make that carbon oxygen pi bond? We use our lone pairs, and those two can complement one another to drive the amine to leave, forming this oxonium intermediate as well as an amine. This amine can then deprotonate the oxonium, forming the neutral ketone as well as, the ammonium. So it is a primary amine, but in the presence of acid, it's going to get protonated. And so what we're going to have is an ammonium and a ketone product. Okay. And as you can see, we did throw water in there initially, and that water was split up, and that was the source of our oxygen in the ketone. So that's why it's called hydrolysis. So hydrolysis with enamines is going to look a little different. However, it is very similar. And when you're looking at your notes, it's important to note that since these are equilibrium mechanisms, the formation of an imine if you look at that mechanism backwards, that's the hydrolysis mechanism. So that's going to be the case for the hydrolysis of enamines as well. So I've indicated this red proton here as our source of acid. Sorry, I think you can hear my kid, but the lone pair on the nitrogen can actually come down, creating that carbon-nitrogen double bond, and this forces the pi bond between the carbon and carbon. We could either move those electrons to the carbon as a carbanion, or we can move directly to that red proton to protonate it. And when we do just attack that proton, that acidic proton, we form an iminium intermediate. So we've seen this before. We know what to do with it now, as seen above. So water comes in and attacks that electrophilic site, indicated in red. Now this forms, again, the oxonium intermediate, and we can then proceed with our proton transfer to shuffle the proton, remove it from the oxygen, and then add it to the nitrogen. This again creates our leaving group in the form of the amine, and we can use the pi electrons or the lone pair on the oxygen to force that amine to leave by creating that carbon oxygen double bond, which again is kind of getting to our final product of the ketone. And so this dimethylamine leaves, which can then remove that final proton on the oxonium intermediate, and this gives us our cyclohexanone as well as dimethylamine. Okay? So this can also be written in a scheme form with the equilibrium arrows as well as H3O plus, and that's all we need in order to do hydrolysis with amines, or enamines, sorry. So hopefully this was pretty clear to you. What we can do now is some practice problems. So what I would suggest to you is, as I write them, you pause the video or you stop it or whatever, and then you try them on your own using the notes or just the knowledge you've gained, and then I'll work through those problems and give you the answers, and then you can compare yours to mine and see what happens. So let's look at benzaldehyde with aniline in mildly acidic conditions and see what we get. Okay, well, So if you paused it, um, what I would encourage you to think about is what these two things are. We have a carbonyl carbon, we have acid, we also have an amine, so a good nucleophile, right? We just need to make it a little better by protonating that oxygen on the carbonyl with that acid, and followed by nucleophilic attack gives us our, I'm going to abbreviate our benzene rings as phenols or pH for simplicity as well as clarity. We have our charged intermediates, then we can do proton transfers, and this will get us to ultimately our final product. So here we go, proton transfer. We've got our lone pair on our nitrogen that can force that water to leave and form our iminium intermediate. Let's see what that looks like. We've got our carbon nitrogen double bond with the nitrogen having 4 bonds. That's why it's got the positive charge. Then we can remove that proton to get to our imine product. So remember, anytime you have a carbonyl and anytime you have a carbonyl and a primary amine, you will form an imine product. Okay, so you could technically just jump straight to this imine product, which eventually you'll be able to do, but it's really important that you understand the mechanism behind it. Okay, and the logic behind it as well. Let's take a look at this cyclopentanone starting material. With what reagent can we get an enamine? Okay, so what we just learned was, I'll pause that real quick, and then when you come back, we'll go over the answer. So what we just learned was that enamines form from carbonyl groups as well as secondary amines, right? And so it's really important that we can look at this enamine and notice that that nitrogen is bound to a carbon with a double bond, right? And that carbon-carbon double bond is the site of the carbonyl carbon. So the one I've indicated in red is the location of that carbonyl. So if we were going to cleave that carbon-nitrogen single bond between the red and the red carbon and the nitrogen, that is going to be the site that we will create a double bonded carbon double bonded to oxygen, as well as just add a proton to that nitrogen. And so it would be a couple steps, obviously, but we have our cyclopentanone as well as our cyclic amine. So let's try another one. Cyclopentanone with what reagent gives you the imine product? So notice this again, I've highlighted in red that carbonyl carbon. And since we have a nitrogen with only one group on it, that's indicative of a primary amine, which would give us an imine product. And so working backwards a little bit easier in this case. And so we've got our carbonyl as well as methylamine. So this one right here is a little bit more complicated. It's going to be a multi-step synthesis. And I want to know how you get from this alcohol to the final product. So take a minute to try and figure that out on your own, and let's see what you get. Okay, but what I would say is we do have an enamine product, and so now we know how to make those. We have a secondary amine as well as a carbonyl group, and so where is that carbonyl group going to be? It's going to be the carbon that is highlighted in red, and so we've got this cyclic ketone here, and as well as a secondary amine. The secondary amine is going to be that cyclic amine that we saw just a minute ago, as also drawn here. So the question would be, we can throw in the amine as our source of, and we can essentially throw in any amine that we want. We don't have to know how to make that amine, but we do not have to know how to make that cyclic ketone or the bicyclic ketone. So how can we make that from this alcohol? Well, we do know how to make ketones, and that was pretty much chapter 17, right? So if we take an alcohol and we oxidize it, we throw in an organolithium or a Grignard reagent, we can make an alcohol, and then we can oxidize it again to a ketone. So this is what I mean, oxidize to an aldehyde, and then we can throw in lithium cyclohexane. And then this nucleophilic organometallic reagent can attack the aldehyde, and after getting protonated with water, we get an alcohol. So this secondary alcohol we know can then be oxidized to a ketone. And so the oxidation steps in this particular reaction, we can use PCC for the first oxidation step, and we actually have to use PCC for that step because PCC, remember, directly or selectively oxidizes primary alcohols to aldehydes. And then we can, for the second one, the second oxidation to get to a ketone, we can oxidize with PCC or that sodium dichromate with sulfuric acid and water. Okay. It's just important to note that you cannot use any other reagent to oxidize other than the PCC initially. Okay, and then so there you have it. There's our final product with a little bit of multi-step synthesis thrown into the mix. What I want to do is, since we're breaking these down into sections, is give you homework questions that are related to addition reactions with amines. So the following homework questions are going to be related to enamine and imine formation, as well as hydrolysis of those two products. So if you have any questions, please let me know. And don't worry, the videos will improve. This was the first one, so I imagine I'll improve drastically over time. So let me know if you have any questions. Let's keep our conversations alive. And just as normal as possible. So we can use the discussion board. We can also use email, and preferably the discussion board. That way we can all work together and still have that conversation going. Okay. If you have specific questions, what I want you to do is email me, and I'll put them all together. Hopefully there's a lot of similar ones, so it wouldn't take me very long, but if they're all different, that's fine too. But I'll put them all together in a video, almost like we were in office hours. And so this is how I'm going to formulate my office hours. So shoot me questions, and I'll try my best to answer them as quickly as possible. Putting together these videos is taking more time than I had hoped or thought, but I imagine that with as I kind of grease up some of the gears in this moving process, I think it'll get a little bit better. So again, let me know if you have any questions and or suggestions. But yeah, have fun. Oh, I forgot to give you a corny joke for the day. So what do you call a pig that does karate? What a pork chop. Boom. Mic drop. I'm out.